The ninth question that we have, actually there are two questions. These two are two independent questions. I just wanted to discuss this tricky question. Question number B. We've been given, let us discuss this one first. This is a rate constant for the reaction A to B is given to be 2 into 10 raised to the minus 4 liter mole inverse minute inverse. Concentration of A at which rate of reaction is this much, we need to find out that. Now for this question people would think, how do we find out the order of the reaction? Now always remember that the order of the reaction is found out by the unit of the rate constant. The unit of the rate constant which comes rate of reaction is equal to K times concentration of A to the power some m. Now this, the unit of K will depend on the m, because if m changes, the unit of this quantity will change, and therefore the unit of K has to adjust, so that becomes equal to the rate of reaction. The unit of rate of reaction, that is mole into second inverse, molarity into second inverse. Now looking at this formula, this is coming out to be liter upon mole minute. This minute is fine, it will give the dimensions of time, but overall we need a dimension of mole per liter over here. Therefore it must be mole per liter into mole per liter, so that this cancels out and gives us mole per liter. Therefore the m should be equal to 2 over here. Therefore by looking at the unit, we found out that the order of A with in the reaction is 2. Therefore we can now write 2 into 10 raised to the minus 4 into concentration of A whole square. This is equal to 1 upon 12 into 10 raised to the minus 5. Now again one thing, this rate is given in minute inverse and this is given in second inverse. This is where students commit mistake. Therefore we should divide this by 60 so that to convert it into second inverse. On solving this, we get 4 into concentration of A whole square is equal to 1. Therefore concentration of A comes out to be equal to half m, that is equal to 0.5 m, which is our answer for the concentration of A at which the rate of reaction is this much. So final answer is concentration of A is equal to 0.5 m. So now let us solve the A part of the question, which is an independent question. We have been given hydrogenation reaction is carried out at 500 Kelvin. The same reaction is carried out in presence of a catalyst at same rate at 400 Kelvin. We need to find out the activation energy of the reaction if the catalyst lowers energy barrier by 20 kilojoule per mole. So you must first understand what a catalyst does. What a catalyst does is it always reduces the activation energy. Now we have been given that an important information is that at same rate, the rate of the reaction is same at 400 Kelvin and 500 Kelvin. We know that the rate of reaction is equal to rate constant into concentration of reactants. Now assuming this to be same, the rate of the reaction is same. When this is not given, we have to assume this to be constant. Therefore the rate of reaction is same means that the rate constant is constant, or rather same at the two temperatures. Now we know that the formula for rate constant is A into e raised to the minus EA upon RT. Now this does not change with temperature. Now at the two temperatures 400 Kelvin and 500 Kelvin, we have the value of K to be same. Therefore the value of EA upon RT at two temperatures should be same, that is EA upon EA at 400 Kelvin upon temperature, that is 400 Kelvin, should be equal to EA at 500 Kelvin upon 500 Kelvin. Now we know that the catalyst has lowered the energy barrier by 20 kilojoule per mole. Lowering the energy barrier means lowering the activation energy. Therefore at 400 Kelvin we can write EA 400 is equal to EA 500 minus 20. Now from here we get that EA 400 is equal to 4 by 5 times EA 500. On substituting this here, we get this can be written as 4 by 5 times EA 500. Now using this we get EA 500 by 5 is equal to 20. That is activation energy at 500 Kelvin comes out to be equal to 100 kilojoule per mole. Now, therefore we get a final answer as the activation energy of the reaction at 500 Kelvin is 100 and at 400 Kelvin is equal to 80, and this is our final answer.